Everyone assumes they know which planet would kill them fastest. Venus sounds obvious. Acid clouds, crushing pressure, heat that never quits. Mars seems manageable if you're optimistic enough. The gas giants you probably write off as a long fall into nothing. But the most obvious threat on each planet is almost never the one that actually ends you. It's the second danger, the one you weren't accounting for because the first one had your attention. Strip away the assumptions. What's left is a precise, unforgiving answer for every world. This is what would actually kill you on each planet in our solar system. Mercury seems like a straightforward heat problem. It isn't. Yes, the daytime surface reaches 430 degrees Celsius, hot enough to melt lead, roughly 4 times beyond what NASA's most advanced suits can handle, which top out at around 121 degrees Celsius. Landing during the day kills you immediately. But here's what most people don't account for. The night side is just as lethal. Without a real atmosphere to retain any warmth, temperatures on the night side collapse to minus 180 degrees Celsius. The suit's lower thermal limit sits at around minus 157 degrees Celsius. You are outside the survivable range in both directions. The heat was never the only problem. It was just the more obvious one. The narrow option is the terminator zone, the thin band between day and night where temperatures sit in a range the suit can theoretically handle. That sounds like a solution until you factor in the timing. Mercury rotates so slowly that a single Mercurian day lasts approximately 59 Earth days. The terminator zone moves on that schedule. And it does not wait. One miscalculation in your landing window and you drift into either extreme before you can correct. Assume you land it perfectly. You are now absorbing nearly 7 times the solar radiation that reaches Earth's surface, with almost no atmospheric filtration. Mercury's exosphere is too thin to deflect anything meaningful. Radiation poisoning becomes your slow background threat while you are busy managing temperature. The cratered, cliff-broken terrain makes a clean landing structurally difficult, and the near-total lack of air resistance makes deceleration harder than it should be, raising the probability of a high-speed impact before any other threat gets a turn. On Mercury, what kills you is the window. There isn't one. Venus looks dramatic from the outside, and for once that appearance is not misleading. As you descend toward the surface, the first thing you meet is the cloud layer. Continuous, dense, and composed almost entirely of sulfuric acid droplets, not a light chemical mist, a highly corrosive substance that destroys organic tissue in seconds. Your lungs would be gone before the information reached your brain. Let's assume your suit filters it completely. You pass through the clouds and visibility drops toward nothing as you enter the lower atmosphere, which is so thick with carbon dioxide that light barely penetrates it. Only about 10% of incoming sunlight reaches Venus's surface. You are descending into dim, chemically hostile near darkness, and the hard part hasn't started yet. The heat finds you next. Venus holds the highest average surface temperature in the solar system, 465 degrees Celsius, held constant by a greenhouse effect so total that the night side is nearly as hot as the day side. Then the pressure arrives. At the surface, Venus's atmospheric pressure reaches approximately 92 bars. Earth's sea level pressure is 1 bar. The equivalent pressure on Earth exists several hundred meters below the ocean surface. A well-engineered pressurized suit might survive a few seconds before the compression becomes structural failure. When the suit goes, the sulfuric acid you filtered out on the way down becomes the air you breathe. On Venus, what kills you is the layering. Every solution you brought exposes the next threat waiting beneath it. Mars has earned its reputation as the most survivable planet in the solar system, and that reputation is accurate in exactly the way a technicality is accurate. Daytime temperatures in equatorial regions can reach a relatively tolerable 20 degrees Celsius. Gravity sits at 38% of Earth's. The surface is solid, navigable, geologically familiar enough to land on without exotic engineering. Mars is survivable the way a room with no exits is survivable. Until something goes wrong, and then it isn't. The atmosphere is the first structural problem. Surface pressure on Mars sits at less than 1% of Earth's. Exposed skin in that environment begins ebulism almost immediately. The moisture in your lungs and eyes vaporizes as pressure drops below the Armstrong limit. The carbon dioxide dominant air composition handles whatever the pressure doesn't. The radiation situation is worse. Mars has no global magnetic field and an atmosphere too thin to filter incoming solar and cosmic radiation. Surface radiation averages between 24 and 30 rads per day, approximately 40 to 50 times the average exposure on Earth. Long-term accumulation reaches lethal doses faster than any realistic mission timeline could accommodate. And then the dust storms come. Martian storms can expand to cover the entire planet within weeks, sustaining winds up to 100 kilometers per hour for months at a time, carrying fine silicate particles that degrade equipment seals, collapse solar power generation, and reduce visibility to near zero. The storm doesn't kill you directly. It disables your life support one component at a time until something critical fails at the wrong moment. Mars is the best option this solar system offers. The best option still kills you. It just takes longer and offers you more time to think about exactly how. Jupiter has no surface. That fact sounds abstract until you understand what it means structurally. There is no destination, no ground to aim for, no defined boundary, where atmosphere ends and planet begins. You are not landing on Jupiter. You are falling into it through layers of increasingly hostile chemistry and pressure, with no endpoint except compression. And the planet starts killing you before you reach the atmosphere at all. Approximately 300,000 kilometers from Jupiter's cloud tops, roughly the distance between Earth and the Moon, the radiation environment becomes lethal. Jupiter's magnetic field is 14 times stronger than Earth's and traps high-energy particles in belts dense enough to penetrate standard spacecraft shielding and begin destroying cellular DNA within minutes. Let's assume your suit handles it. You continue falling. The uppermost cloud layer greets you with frozen ammonia crystals at around minus 150 degrees Celsius and sustained winds of approximately 482 kilometers per hour. These are not storm conditions. This is Jupiter's permanent atmospheric baseline. You fall through it. Around 150 kilometers below the cloud tops, you reach the deepest point ever explored. The depth NASA's Galileo probe achieved in 1995 before pressure and heat ended the mission. Pressure there was already several times Earth's surface level and accelerating. Below this, the atmosphere darkens and thickens into a supercritical fluid, a state that is neither gas nor liquid, but shares properties of both. Moving through it would feel like forcing yourself through something dense and resistant. Except every seal on your suit is being tested simultaneously from all directions. Deeper still, pressure climbs to approximately 1.4 million bars, and hydrogen transitions into metallic hydrogen, a phase of matter with no natural Earth equivalent, conducting electricity like a metal while flowing like a liquid. You do not pass through this layer. It traps you, the density and electromagnetic properties making forward movement physically impossible. Not that it matters. If you somehow cleared it, Jupiter's core sits at an estimated 24,000 degrees Celsius, roughly 4.5 times hotter than the surface of the Sun, surrounded by pressures estimated at around 100 million times Earth's atmospheric pressure. On Jupiter, what kills you is the architecture. Every layer is a different mechanism, and none of them have exits. Saturn kills you on the approach, which at least has the decency to be spectacular. Its ring system, fed by debris from shattered moons, compressed ice, rock fragments, and asteroid material, extends tens of thousands of kilometers outward and requires navigation precise enough to put serious stress on any spacecraft. Let's assume you thread it without a collision. You reach Saturn's equatorial atmosphere and immediately encounter sustained winds of approximately 1,800 kilometers per hour. The most powerful hurricanes recorded on Earth peak at around 300 kilometers per hour. Saturn's baseline is 6 times that. Your suit, your craft, and any structure connected to you faces continuous mechanical stress from the first moment of atmospheric contact. There is no calmer entry corridor. The equator is the better option. Attempting entry from the North Pole avoids the equatorial winds and introduces something considerably worse: a persistent hexagonal storm system so large that 2 Earths fit inside its boundaries, with internal wind speeds severe enough to make controlled descent effectively impossible. Temperatures in the upper polar atmosphere sit at around minus 250 degrees Celsius. Ammonia clouds dominate the region, similar in composition to Jupiter's upper layers. You descend through either entry point, and, if something on your craft hasn't failed yet, you pass into deeper atmosphere where temperature gradually climbs back toward 0 degrees Celsius, and the gases around you begin transitioning into a liquid state. The pressure at this depth has already surpassed the bottom of Earth's deepest ocean trenches and continues rising without a ceiling. Saturn's core is rocky, molten, approximately 10 times the mass of Earth, and estimated at around 11,700 degrees Celsius, roughly twice the temperature of the Sun's surface, surrounded by pressure approximately 10 million times greater than Earth's atmosphere. On Saturn, what kills you is persistence. The planet has enough distinct layers to stop you in several different ways, and it doesn't need to choose just one. Uranus starts killing you before you arrive, which is at least an honest approach. The planet sits approximately 2.7 billion kilometers from Earth at closest approach. A one-way trip using current propulsion technology takes roughly 9 to 10 years. By the time you reach it, you have spent nearly a decade in microgravity, absorbing cosmic radiation with minimal shielding. Running on a closed-loop life support system operating continuously at the edge of its tolerances, and functioning under the psychological conditions of extreme isolation with no possibility of rescue or resupply. You haven't touched Uranus yet, and you are already a compromised system. Then, you reach the rings, narrow, dark, requiring navigation, and pass into the outer atmosphere, where temperature drops immediately to around minus 220 degrees Celsius. This makes Uranus the coldest planetary atmosphere in the solar system, colder than Neptune despite Neptune sitting considerably farther from the Sun. The reason is simple and strange. Uranus generates almost no internal heat. Other planets radiate warmth outward from their cores. Uranus does not. It is cold all the way down. Being an ice giant does not mean Uranus is a solid frozen surface waiting to receive you. The term describes chemical composition, elements heavier than hydrogen and helium, including water, ammonia, and methane compressed into exotic states. Not physical structure. There is no ground. Like the gas giants above it in this list, Uranus swallows you. The outer atmosphere is hydrogen and helium. Below that sits a mantle of water, ammonia, and methane ices under pressures that have no Earth analog. It is within this mantle, at pressures estimated around 1 million times Earth's atmospheric pressure, that something extraordinary and completely fatal occurs. Pressure breaks down methane molecules, separating carbon atoms and compressing them into crystalline structures. Diamonds form and fall as precipitation through the interior. You are inside a diamond rainstorm, which would be the most spectacular thing a human being has ever witnessed, happening at pressures that ended your life a significant distance above the depth where it occurs. The diamonds are not the weapon, the pressure producing them is. At the depths where diamond rain falls, atmospheric pressure sits at approximately 100 times Earth's surface level, enough to collapse any suit material currently in development or theoretical planning. On Uranus, What kills you is the cold. It reaches you in the outer atmosphere, long before the interior ever gets a chance to be impressive. Neptune is Uranus, with the restraint removed. It orbits approximately 4.5 billion kilometers from the Sun, roughly 30 times the Earth-Sun distance, which means incoming sunlight is around 900 times dimmer than what Earth receives. You arrive in near darkness, approaching a planet layered in deep blue methane haze, descending into an outer atmosphere sitting at around minus 200 degrees Celsius. The cold is familiar. What isn't familiar is the wind. Neptune's winds are the fastest measured on any planet in the solar system, reaching approximately 2,100 kilometers per hour at the cloud tops, supersonic relative to Earth's atmospheric conditions. Here's what makes that strange. Neptune receives almost no solar energy at that distance. These winds are not driven by sunlight. They are generated by the planet's internal heat, which is substantial enough that Neptune radiates more than twice the energy it receives from the Sun outward into space. Something deep inside it is producing enough thermal energy to sustain weather systems that would structurally dismantle anything you brought with you before you cleared the first major atmospheric layer. The descent mirrors Uranus in composition, hydrogen and helium in the outer layers, then a mantle of water, methane, and ammonia ices under escalating pressure. Diamond rain occurs here as well, driven by the same mechanism. Methane fracturing under extreme pressure, carbon atoms compressing into crystalline form, diamonds precipitating toward the interior. Neptune's version may be more dynamically intense. The internal heat-driving convection means the process is more active, the pressure gradients steeper. You encounter the diamond rain at depths where your suit stopped being structurally sound several kilometers above. Neptune's core sits at an estimated 7,000 degrees Celsius, hotter than the surface of the Sun, surrounded by pressures that compress the planetary interior into states of matter with no earthly equivalent. On Neptune, what kills you is the wind. Everything below the cloud tops is a longer answer to a question you stopped being able to ask almost immediately after arrival. 8 planets. 8 different answers. None of them the obvious one you assumed at the start. The solar system doesn't deal in the threats you prepared for. It deals in the ones directly behind them.